In this video, I'm going to explain how to use the QURI SDK to execute the QSCI algorithm. So first, let me give you a brief introduction on what the QSCI algorithm is. The QSCI algorithm is a quantum algorithm for you to estimate the eigenenergies of a given Hamiltonian. Most of the time, it is used to estimate the eigenenergies of a molecular Hamiltonian. You can scan the QR code here to get access to its original paper. There are a couple of advantages of the QSCI algorithm. First, it is noise resilient in the sense that the quantum computer is only used for sampling and determining the subspace of the Hamiltonian. And the diagonalization is done on a classical computer, so this part is error-free. Also, it does not need to compute the Hamiltonian expectation value and its gradients. So, it means that you only need a smaller shot count compared to using the VQE algorithm. And it has been tested in various circumstances that it can perform well even on strongly correlated systems. The QSCI algorithm has been selected to be one of the first algorithms to be released in the IBM Qiskit function catalog, where you can access it by scanning this QR code over here. And there, we demonstrate a 36-qubit strongly correlated system, and the dissociation curve was reproduced faithfully. Now, let me get down to the algorithm itself. Suppose you have a way to prepare a quantum state on a quantum circuit. Then you can sample this state on the computational basis. From the sampling results, you can choose to accept or reject particular computational basis states based on the symmetry of your system and its importance. Then you construct an effective subspace Hamiltonian based on the sampling results and the original Hamiltonian H. Finally, you diagonalize this effective Hamiltonian, and the eigenenergies you get is the estimation of the spectrum of the original Hamiltonian. To run the QSCI algorithm with the QURI SDK, let's first install some dependencies. First is QURIPart's PySCF package. It helps you build the molecule, perform the Hartree-Fock computation, and compute the electron integrals. These are important ingredients for building a molecular Hamiltonian. Next is the QURIPart's OpenFermion package. It helps you take the elements that you compute with the PySCF package in the last step and explicitly builds it into a molecular Hamiltonian. Then, we install the QURIPart's Qiskit package. It helps you transpile your circuit and run on a NISQ device, and in particular, an IBM device. And finally, we install the QURIPart's QSCI library, which is the one that contains the major QSCI algorithm. In the next step, let's set up the molecule that is going to be used in this video. We do so by introducing this molecular information class. This class is a wrapper for creating the molecule, computing the molecular Hamiltonian, and it is going to help us prepare the initial state that is going to be an input of our QSCI algorithm. The state preparation method used here is the UCCSD ansatz with the CCSD initial parameters. There are a lot of methods provided here, but the most important ones are the Hamiltonian, which gives you the molecular Hamiltonian of the molecule that you're interested in. And also, at the bottom of this class, we have the prepare QSCI state method, which prepares the input state of your QSCI execution. Our interest here is the azobenzene molecule. The azobenzene molecule has two isomers. One is the trans azobenzene, and the other is the cis-Azobenzene. And the transition between these two isomers can be induced by photons. This procedure is interesting in that this property can be used as a molecular switch. So I'm going to compute the ground state energy of both molecules, and then I will show you the energy gap, the overlap, and the precision of the QSCI algorithm. The coordinates of the two isomers can be downloaded from the PubChem website, and we can visualize it here. As it is a large molecule, we can identify the active space relevant to the photon-induced transition. The lone pair on the nitrogen atoms here and here is particularly important for the transition. So the active space here is chosen around the HOMO, the LUMO, and the lone pair on the nitrogen atoms. With this at hand, we can build our molecule with the molecular information class that we constructed in the last block. With the molecular information here, we can start to execute the QSCI algorithm. But before then, we can first compute the exact ground state energy by exactly diagonalizing the molecular Hamiltonian, which is performed right here. Here, this trans GS energy corresponds to the cis-Azobenzenes molecular Hamiltonian's ground state energy, and this is its corresponding eigenvector. This is similar for the cis-Azobenzene. Now, we start executing the QSCI algorithm. We first import the QSCI algorithm from QURI parts QSCI. And as we know from the beginning of this video, the QSCI algorithm needs to take in the problem Hamiltonian, a prepared state, a sampler, the number of shots, as well as the subspace Hamiltonian size denoted as R. So we set up these parameters here. In our case, where there are 8 active electrons, 6 active spatial orbitals, the cis-CI space is of dimension 225. For QSCI to be meaningful, we need to choose the subspace dimension much smaller than that of the cis-CI. Here, we pick the subspace dimension to be 20, which is smaller than 1/10 of the cis-CI space. The number of shots is chosen to be 100,000. For the sampler, we use the QLAX state vector sampler, which corresponds to sampling on a noise-free device. Let's run the function with these settings right now. The first return value is the QSCI energy, and the second is the important computational basis states identified by the QSCI algorithm and their corresponding amplitudes. We can translate it into a NumPy array and compute its overlap with the exact ground state eigenvector. Here, we can see that the energy error is smaller than 1 millihartree. This falls into the chemical accuracy. The overlap can be visualized by the following plots, where the height of each bar corresponds to the amplitude magnitude square of the electron configuration. The same can be repeated for the cis-Azobenzene, where we use the exact same setting for the QSCI algorithm. We find again that QSCI faithfully produces the ground state energy and the state vector, and its overlap can again be visualized with this bar plot over here. Lastly, we perform QSCI simulation assuming we execute the circuit on a noisy NISC device. To do so, we only need to replace the previous noiseless sampler with a noisy one. However, we need some work to construct the noisy sampler. First, we need to build the noise model. We assume the dominating source of error comes from the depolarization error with error probability being 10 to the minus 3. However, our circuit consists of multi-Pauli rotation gates, which is usually not directly available on a quantum computer. Thus, we need to transpile it to the basis gates that a NISC computer can process. Thus, we use the Qiskit transpiler here. We set the optimization level to be 3 so that the circuit is heavily optimized before execution. This is not the end of the story. For QSCI to work well, we hope to discard those states that do not respect the symmetry of the Hamiltonian. In this case, the symmetry is that the Hamiltonian conserves the electron number and the SD quantum number. So, we create a filter function to filter out those states that respect the conservation law. Any basis state that does not will be forcefully removed. So, we decorate the noisy sampler with the filter function. Usually, the UCCSD ansatz is very deep, while the CCSD amplitude is sparse. This means that there are lots of rotation gates in the UCCSD circuit that are very close to an identity operation. These gates serve no other purpose than introduce noise that corrupts our QSCI performance. So, we forcefully remove the gates from the UCCSD circuit with a small rotation gate, and the cutoff we choose here is 10 to the minus 2 for faster simulation. Now, we have all the ingredients ready. We can perform the noisy simulation for both isomers of azobenzene. The code here is the same as before, except that the sampler is replaced with a noisy one that we constructed here. The subspace dimension is also increased to 100 to boost the performance. Comparing the results with the exact energy and the noiseless QSCI energy, the energy error seems to be a little bit large. This can be improved by more advanced error mitigation techniques such as configuration recovery, or we need to execute the algorithm on a better device with error correction support. In the next video, we will show how much the circuit fidelity increases if we have a fault-tolerant device available even if the error correction is done only partially.